Okay, so I want you to imagine you're standing on a street corner. Let's say, I don't know, Fifth Avenue and 34th Street in Manhattan. Or maybe you're deep in the financial district in Hong Kong with that dense, humid energy all around you. You just stop walking for a second, and you tilt your head back to look at the building right in front of you.
And you keep tilting.
You keep tilting. You tilt your head back until your neck actually starts to hurt, until you can feel the vertebrae kind of crunching a little bit. And you're looking up at this just sheer cliff face of glass and steel that seems to just disappear somewhere into the clouds.
It's really the defining image of the modern city, isn't it? But if you stand there long enough, looking up at that angle, you start to realize something a little unsettling. You realize that you're a biological organism, a soft, relatively fragile, hairless ape standing at the base of a 1,000,000-ton needle that is, for all intents and purposes, balancing on a pinhead.
A needle that's actively fighting gravity, fighting the wind every second of the day, and it's housing thousands of other hairless apes. And yet, what do? We walk inside, we press a button, we shoot up 100 floors to go grab a latte, and we don't even blink.
We've completely normalized what is, objectively, an impossible feat of engineering.
That is exactly what we're doing today. We are stripping back the skin of the city to do a deep dive into the skyscraper. And I want to be really clear about our mission here. This isn't just going to be a list of the top 10 tallest buildings. We're not doing the tourist tour.
No, absolutely not. We're looking for the engineering breakthroughs. We really want to dig in and identify the specific mechanical and physical problems that had to be solved, the bottlenecks that basically stopped us for thousands of years.
And the aha moments.
And the aha moments, exactly. The flashes of genius that finally allowed us to, live and work in the clouds.
We're going to talk about the transition from, say, mud brick towers in the middle of the desert to these modern tube structures and these crazy aerodynamic damping systems that are letting us break the kilometer mark. We've got a whole stack of source material here, architectural histories, engineering journals, even some physics breakdowns of wind vortices.
And what's so fascinating when you look at it all together is that the history of the skyscraper isn't this clean, straight line of progress. It wasn't just, oh, we got better at building. It was a series of hard stops. Physics would throw a problem at us, we'd get stuck for a few centuries, and then someone, somewhere, would have a truly genius idea.
So let's start at the very beginning, or I guess let's start with the ground rules for what we're even talking about. Because when I first started reading through this, the first thing I thought was, okay, the Great Pyramid of Giza, that was the tallest man-made thing on Earth for, what, almost 4,000 years?
It was, yeah. It stands at 146 meters, which is nearly 500 feet. That is a massive, massive structure by any measure.
But according to all the experts, it doesn't count as a skyscraper.
It does not.
Why not? I mean, it's tall, it's man-made, it's iconic. What's the missing ingredient?
It's a tomb. I mean, the technical definition of a skyscraper, if we look at the standards set by the Council on Tall Buildings and Urban Habitat, which is kind of the official governing body for these things, it all hinges on one critical word: habitability.
So you have to be able to actually live inside it.
Yeah.
Or work inside it.
You have to be able to occupy it, yeah.
Yeah.
A skyscraper is fundamentally a machine for human occupation. The Great Pyramid, on the other hand, is a solid pile of limestone blocks with just a few very, very narrow, very claustrophobic tunnels leading to a burial chamber. The structural logic is simple. You just pile rocks until you reach a point.
Okay, that makes sense.
The Eiffel Tower is another great example of this. When it was built in 1889, it just blew everyone's mind. It was the first structure to cross that 300-meter mark, which was a huge psychological barrier.
But you can't live in it. It's a lattice tower.
Exactly. It's an open framework of iron. You can't rent an apartment in one of the girders. You can't have an office on the 50th floor because there is no 50th floor. There's just air and iron beams.
So the real engineering challenge isn't just make something tall, it's make it tall, make it hollow, and then fill that hollow space with heavy people, furniture, plumbing, partition walls, everything.
Precisely. You're stacking usable, rentable volume, not just stacking mass. And that distinction is what makes the history so interesting, because the desire to do this, to stack families on top of each other, is actually ancient.
Right. This is the common misconception. I always assumed it was a purely modern American invention from, the late 19th century, Chicago.
That's what most people think. But the source material points us way, way back to imperial Rome.
Rome. I've had villas and forums, not high-rises.
Well, Rome had a serious population crisis. They were constrained by the city walls, land was incredibly expensive, and they couldn't just sprawl outward. So what was the logical solution? They went up, they developed these apartment blocks called insulae.
And these weren't just like two-story townhouses.
Oh, no. These were high-rises. We have written records from people like the poet Martial and the satirist Juvenal describing them reaching 10 stories or even more.
10 stories in ancient Rome. How do you even build a 10-story building without steel beams or, reinforced concrete?
Poorly. To be honest, very, very poorly. They used a combination of timber frames, sun-dried mud bricks, and a kind of primitive rubble concrete. The engineering was, frankly, terrifying.
I'm picturing something pretty unstable.
You're right, too. They were basically stacking heavy, brittle materials on top of each other without a proper, rigid frame to hold it all together. The structural integrity was, let's say, suspect.
Suspect is a gentle word for it, I imagine.
It's putting it mildly. The poet Juvenal actually wrote about what it was like to walk through the streets of Rome in constant fear. And he wasn't afraid of muggers. He was afraid that a pot would fall off a high ledge and crack his skull, or worse, that an entire building would just collapse into the street.
And that actually happened.
It happened all the time. There were notorious fire traps, too, because they were packed with timber. A fire could take out an entire block.
It got so bad that the emperors had to step in, right? The government had to regulate this.
They did. Emperor Augustus set a height limit of about 20 to 25 meters. That's roughly 80 feet, maybe 7 stories. And it wasn't an aesthetic choice to protect the view of the Forum. It was a public safety measure to stop the death toll. It's probably the first example in history of zoning laws being driven by repeated, catastrophic structural failure.
So the ambition, the economic drive to build high was there, but the material science just completely failed them.
It couldn't keep up. Now, if we jump forward 1,000 years or so to the Middle Ages, we see another fascinating attempt in Bologna, Italy. I've seen the old drawings of this. It looks like something straight out of a fantasy novel.
Yeah, the whole city skyline is just towers.
It really does. In the 12th century, Bologna's skyline looked like a pincushion. It was absolutely bristling with these tall, slender towers. The wealthy families built them as status symbols and for defense. At its peak, there were somewhere between 80 and 100 of them.
And some of them were seriously tall, right? Like modern building tall?
Oh, yeah. The Asinelli Tower, which is still standing today, is 97.2 meters tall. That is nearly a modern 30-story building.
Wow. But again, these weren't really efficient skyscrapers in the modern sense.
No, not at all. Because they were built with masonry, the walls had to be incredibly thick at the base to support that height. So the rooms inside were tiny, dark, and cramped. They were built primarily for defense and status. Basically, my family is more powerful than yours because my tower is taller, not for maximizing rentable square footage.
It was a medieval measuring contest, basically.
Very much so. But if you want to find the true ancestral home of the modern skyscraper city, a place that actually functioned like a vertical, high-density neighborhood, you have to look at a really unexpected place. Yemen.
Shibam. I've read about this. They call it the Manhattan of the desert.
This place is absolutely incredible. It dates all the way back to the 16th century. It's a walled city built in the middle of a desert wadi, a river valley. To protect themselves from Bedouin raids, they couldn't spread out. So again, they went up.
And they built these tower houses out of what, mud?
Sun-dried mud bricks. They rise 5 to 11 stories high.
11 stories made of mud bricks. That seems impossible.
And they're still standing today, hundreds of years later. Now, they require constant maintenance. You have to reapply layers of mud plaster because of rain erosion, but they function as high-density vertical housing. Each floor of a tower house serves a different function for the family that lives there. It's definitive proof that the skyscraper isn't a technology, it's an economic solution to a scarcity of land.
Okay, so we've established the motivation has been there for centuries. Rome, Bologna, 16th century Yemen. So why did it take until the late 1800s for us to really break through and build the cities we see today? What were the hard physical limits?
There were 2 absolute bottlenecks. One was structural, and the other was, for lack of a better word, physiological.
Let's tackle the structural one first. The source material calls this the masonry problem.
Right. In all traditional construction, from the pyramids to those towers in Bologna, the walls are load-bearing. That means the wall itself supports the weight of the floor above it, which supports the wall above that, and so on, all the way up. The entire weight of the building is channeled down through the walls.
So the higher you go, the heavier the building gets.
Exponentially heavier. And as it gets heavier, the walls at the bottom have to get thicker and thicker to avoid being literally crushed under the compressive load. It's that pyramid principle again.
And eventually you just hit a point of diminishing returns where it doesn't make sense anymore.
You do. And that practical limit was reached in Chicago with the Monadnock Building, which was completed in 1891. It's 16 stories tall, which was absolutely massive for its time. But to support those 16 stories of brick, the load-bearing walls at the ground floor are 6 feet thick.
6 feet. That's wider than I am tall.
6 feet of solid masonry. Now imagine, you're a shop owner on the ground floor. You want big, beautiful display windows to show off your goods. You want wide open floor space for your customers. But instead, you have these tiny tunnel-like entrances and walls that are eating up half of your rentable area. You literally couldn't go any higher because the building would eventually just become a solid brick pyramid at the bottom.
So that's the hard structural ceiling. What was the physiological problem?
Stairs.
It's that simple.
It's that simple. Before the mid-19th century, verticality was a punishment. If you lived on the 7th floor of a tenement building in, say, 17th century Edinburgh, which also had high-rises out of necessity, you were almost certainly destitute. You had to haul your water, your coal, your groceries up 7 flights of stairs every single day.
So the penthouse wasn't a luxury item.
Far from it. The rich lived on the 1st or 2nd floor, the piano nobile, the noble floor. The poor lived in the garrets and attics at the very top because it was cheap, it was hot in the summer, cold in the winter, and absolutely exhausting to get to.
So to get to the modern skyscraper, we needed to solve the wall problem and the stair problem. And this brings us to what the outline calls the technological trinity. These 3 key inventions that all converged between roughly 1850 and 1890 to make the modern skyline possible.
The safety elevator, the steel frame, and the curtain wall, the holy trinity of vertical construction.
Let's start with the elevator. We always credit Elisha Otis, but hoists and lifts existed before him, didn't they?
Oh, sure. Steam-powered hoists were used for moving cargo in factories and warehouses, but they were absolute death traps. They were lifted by a single hemp rope. If that rope snapped and hemp ropes frayed and snapped all the time, the platform just plummeted and whatever was on it was destroyed. You would never put a human being on one of those.
So what was Otis's great innovation?
Elisha Otis didn't invent the elevator. He invented the brakes, the fail-safe.
This is the famous Crystal Palace demonstration, right?
1853, at the Exhibition of the Industry of All Nations in New York. It's pure showmanship. He gets on this hoisting platform, has it raised high above the crowd, then he dramatically orders his assistant to cut the single supporting rope with an axe.
The crowd must have freaked out.
They gasped. They thought they were about to witness a man plummet to his death, but the rope is cut and the platform drops just a few inches and then stops dead with a loud clang. He tips his hat and says, "All safe, gentlemen. All safe."
How did it work? It seems like magic.
It was a brilliantly simple mechanical solution. He used a large leaf spring mechanism at the top of the elevator car. While there was tension on the rope as it was pulling the car up, that tension held the spring in a compressed state. But the moment the rope was cut, the tension vanished. The spring was released, and it snapped outward.
And it grabbed onto something.
It engaged these heavy-duty ratchets like big metal teeth that physically clawed into the guide rails on either side of the elevator shaft. The system works because the main rope fails. It's a true fail-safe.
And that one demonstration completely changed real estate economics forever.
Overnight, the upper floors went from being the least desirable to the most desirable.
Yeah.
You got better light, you got cleaner air away from the horse manure and noise of the street, you got the incredible views. The entire concept of the penthouse was born the moment Elisha Otis cut that rope.
Okay, so now we can get people up there safely. Problem 1 is solved. But we still have the 6-foot-thick walls. We need to get rid of the masonry problem.
And this is where the Industrial Revolution provides the other key ingredient, steel.
We moved from building with stone, which is fantastic in compression but terrible in tension. It cracks if you pull it. To steel, which can handle both forces beautifully.
Exactly. But the real architectural breakthrough wasn't just the material. It was shifting the entire load path of the building. In 1885, an architect in Chicago named William LeBaron Jenney was designing the home insurance building. And he had a radical realization. Instead of stacking heavy bricks, why not build a rigid cage first?
A skeleton.
A skeleton. A 3-dimensional grid of iron and later steel columns and horizontal beams, all bolted or riveted together. This cage, this internal skeleton, carries the entire weight of the building. The walls suddenly stop doing the heavy lifting.
They stopped doing any lifting at all.
Which leads directly to the third innovation, the curtain wall.
I love this term because it sounds so delicate and decorative, but it really represents this massive engineering shift.
It is absolutely radical because the steel frame is holding the building up. The outer walls are just hanging off the frame like curtains. Their only job is to keep the weather out and the people in.
So you can make them out of anything.
Anything lightweight. You could make them out of thin panels of stone, terracotta, aluminum, and this is the crucial part for the 20th century glass.
This is why that building in Liverpool, Oriel Chambers, built way back in 1864, is so important, even though people at the time apparently hated it.
Oh, they despised it. One critic called it a large agglomeration of protruding plate glass bubbles. It was hideous to the Victorian eye, which was used to solid, heavy masonry. But Peter Ellis, the architect, had proved the concept. You could have a metal frame with a glass skin. No more dark, thick-walled fortresses. The building could be light, it could be airy, it could be transparent.
So the Trinity is complete. We have the steel frame to hold it up, the glass curtain wall to let light in, and the safety elevator to get us to the top.
Yeah.
The stage is officially set.
The ingredients are all there. Now you just need the ambition.
And the ego.
And yes, always the ego.
Which brings us to the great rivalry between New York and Chicago in the late 19th and early 20th centuries. This was the golden age.
It really was a tale of two very different philosophies. You had the Chicago School, led by architects like Louis Sullivan and Daniel Burnham. They were obsessed with the logic of the steel frame. They believed form should follow function.
Right. This is Sullivan's famous quote. He said, "A tall building must be every inch a proud and soaring thing."
Exactly. He wanted to emphasize the verticality. He didn't want it to look like a classical column with a base, a middle, and a top. He didn't want it to look like a layer cake. He wanted to celebrate the sheer height that the steel frame made possible.
But New York had other ideas.
New York was just feral. New York was pure, uncut capitalism and spectacle. It became a literal, publicly waged race for the title of world's tallest building. And the absolute climax of this era was the insane battle between 40 Wall Street and the Chrysler Building in 1929 and 1930.
This story is wild. You had the architect of 40 Wall Street, H. Craig Severance, and the architect of the Chrysler Building, William Van Allen. And they used to be partners, right?
They were former partners turned bitter rivals. It was incredibly personal. So Severance finishes 40 Wall Street, and it's officially taller than the previous record holder, the Woolworth Building. He declares victory. He thinks he's won. He'd seen the public plans for the Chrysler Building and calculated that his building was taller, but Van Allen had pulled a fast one.
He was hiding a secret weapon, a trump card.
He had been secretly assembling a 125-foot stainless steel spire called the Vertex in sections inside the fire shaft of the Chrysler Building. Nobody on the outside knew it was there.
So he was basically building a cathedral spire inside the building's chimney.
Effectively, yes. So the day that 40 Wall Street is certified as the world's tallest building, Van Allen gives the signal. Construction workers on the top of the Chrysler Building hoisted the first piece of this massive spire up through the roof and then pieced it all together.
In the open air.
Hundreds of feet above Midtown Manhattan. In the space of about 90 minutes, the Chrysler Building grew by 125 feet and completely stole the title.
That is the single greatest architectural mic drop in history.
It truly was. But it turned out to be a very short-lived victory, because just a few blocks away, something else was rising, something that would dwarf them both. The Empire State Building.
And that building was just a monster. It was on a completely different scale.
First building ever to pass 100 floors. First building over 1,200 feet tall. But what's still baffling to modern engineers is the speed of its construction.
I read this and I couldn't believe it. They were building 4.5 stories a week.
A week? It's almost incomprehensible. The entire project, from the first steel beam to opening day, took just over a year.
How is that even physically possible?
It was a masterpiece of logistics, like a military operation. They had a miniature railway system on the site to move materials. The steel beams would arrive by train from the foundries in Pittsburgh, still warm to the touch, and they would be hoisted and riveted into place within 80 hours of being made.
And the workers, the famous photos of them.
You had teams of Mohawk iron workers, the Skywalkers, who were completely fearless. You had teams of riveters tossing red-hot metal bolts to each other hundreds of feet in the air. It was incredibly dangerous, it was deafeningly loud, and it was unbelievably efficient.
And it opened in 1931. In the depths of the Great Depression, and just absolutely crushed all the competition.
It held the world record for 40 years. 40. That is an unprecedented length of time in the skyscraper game. Nothing came close.
But then, there's a long silence. The Great Depression hits, then World War II. We basically stopped building giants for a couple of decades.
The economics just weren't there. But when we started to get ambitious again in the 1960s, the engineering logic of the simple steel frame, the kind used in the Empire State Building, hit a brand new wall.
So we're back to bottlenecks again.
We are. You see, the Empire State Building is a steel frame, but it's a brute force steel frame. It's packed with steel, it's incredibly heavy, and by modern standards, over-engineered. As you try to go higher, the wind forces increase exponentially.
Right, the wind is worse at the top.
Much worse. And to keep a traditional frame stiff enough so it doesn't sway like a giant metronome in that wind, you have to add so much diagonal steel bracing that it becomes wildly expensive, and the interior columns get so big and so numerous.
You lose the floor space again. The columns eat the office.
Exactly. You're back to the Monadnock building problem, but with steel instead of brick. By the 1960s, it was clear that if you wanted to go higher than the Empire State Building, the old cage method just wasn't going to work. We needed a new paradigm, a new way of thinking about the structure itself.
Enter the hero of our engineering story, Fazlur Rahman Khan.
The Einstein of structural engineering. He is an absolute legend in the field.
I have to admit, I hadn't heard of him before this research, but it seems like he is the single most important figure in the history of the modern supertall skyscraper.
Without a doubt. Khan was a Bangladeshi-American structural engineer working at the firm Skidmore, Owings & Merrill, or SOM, in Chicago. He looked at the problem of tall buildings and realized we were thinking about it all wrong. We were trying to make the inside of the building stiff with all this cross-bracing. He said, why not make the outside of the building stiff?
This is the tube concept.
This is the revolutionary tube concept. His analogy was a bamboo stalk. It's hollow in the middle, but the skin, the exterior, is incredibly rigid and strong. So Khan's idea was to move the primary structural columns to the perimeter, the outside edge of the building, and space them very, very close together.
The exterior wall basically becomes a hollow, rigid tube.
Exactly. And a tube is an incredibly efficient shape for resisting lateral loads, which is engineers speak for wind. The whole building acts like a giant cantilever beam stuck in the ground. And the huge benefit is, because all the strength is on the perimeter, you can clear out the interior. You don't need a forest of columns blocking up the valuable office space.
And he kept iterating on this idea. He developed the truss tube with the John Hancock Center in Chicago.
That's my personal favorite skyscraper. It's just so honest. You know those giant X braces you see on the outside of the Hancock Center?
Yeah, I always just assumed that was an aesthetic choice, some kind of industrial chic look.
Not at all. That is pure, unadorned structural necessity. Those giant X's are the structure. They take the gravity loads and the wind loads and they channel them down the exterior columns with incredible efficiency. It was so efficient, in fact, that the John Hancock Center used nearly half the amount of steel per square foot compared to a traditional frame building of a similar height like the Empire State.
Half the steel. That's a massive cost saving. That makes supertalls economically viable again.
It completely changed the economics, and then for his masterpiece, he came up with the bundled tube.
This is the Willis Tower, or as we Chicago purists will always call it, the Sears Tower.
The Sears Tower. The concept here is just brilliant. Imagine taking 9 cigarettes and holding them together in a 3x3 bundle. Individually, they're pretty flimsy. You could snap one easily. But when you wrap them together, the bundle becomes incredibly rigid. Khan designed the Sears Tower as 9 separate square structural tubes bundled together at the base.
And this solved the wind stiffness problem.
It did, but it also solved a huge aesthetic problem. Because the tubes were bundled, you could terminate some of them at different heights. That's why the Sears Tower has that iconic stepped, setback look. Before Khan and the bundled tube, skyscrapers were basically just boxes. He made it possible for them to be sculptures.
His work really unlocked the modern era of supertalls in Asia and the Middle East, didn't it? The Petronas Towers, Taipei 101, the Burj Khalifa, they all owe a huge debt to his tube concepts.
They are all direct descendants of his thinking. He is the father of the modern supertall.
So the structural problem of gravity and wind stiffness is largely solved by the tube. But as we get into the modern era of the supertall, that's buildings over 300 meters, and now the megatall, which is over 600 meters, we run into a new, more subtle enemy, the air itself.
Wind becomes the dominant force you're designing against. For these megatall buildings, gravity is the easy part. Wind is the monster, and at that height, the wind isn't just a steady breeze. It's a turbulent, chaotic, and incredibly powerful force.
And we need to talk about a specific phenomenon here called vortex shedding. This sounds like some kind of sci-fi technobabble, but it's very real physics.
It is the one phenomenon that keeps structural engineers up at night. When wind hits a big, flat surface, like the side of a square building, it can't just go through it. It has to flow around the sides. As it flows around the corners, it creates these little swirls of low pressure or vortices on the backside of the building.
Kind of like the wake behind a boat in water.
That's a very similar idea. But here's the dangerous part. These vortices don't just sit there. They detach or shed from the building in a very regular alternating pattern. First one sheds off the left side, then one off the right side, then left, then right.
And that creates a rhythmic push and pull on the building.
Exactly. It creates a lateral force that pushes the building from side to side. And if that rhythm, that frequency of the vortex shedding, happens to match the natural resonant frequency of the building itself, you get resonance. The swaying motion amplifies. It gets bigger and bigger and bigger with each push.
Like pushing a kid on a swing at the exact right moment to make them go higher and higher.
Precisely. And in a building, that can compromise the structure, or at the very least make everyone on the 80th floor incredibly seasick.
So how do you fight physics? How do you stop this?
You can't stop it. So you have to trick it. You have to confuse the wind.
Confuse the wind. How do you do that?
You break up the pattern. Look at the Burj Khalifa, the current tallest building in the world. It's not a smooth, straight extrusion. It has that distinctive Y shape, and it steps back in a spiral pattern as it rises. It's constantly changing shape.
I see. So the wind never encounters the same consistent building shape for very long.
Precisely. The vortices that form at 200 meters are a different size and frequency from the ones that form at 400 meters. They never get a chance to organize into one single coherent force that can rock the whole building. You're essentially dismantling the wind's attack. It's aerodynamic spoiling.
And another strategy I've seen on some of the newer, skinnier towers is just letting the wind go through the building.
Blow through floors, yeah. You see this in some of the new pencil towers in New York. And at the top of the Shanghai World Financial Center, the one that looks like a giant bottle opener, they just leave massive multi-story holes in the building. It acts like a pressure release valve. Instead of fighting the full force of the wind, you just let a lot of it pass right through.
Okay, I want to pivot back to the inside of the building again for a minute. Because as we go higher and higher, the Burj Khalifa is 828 meters tall. We run into that old problem, the elevator conundrum, but on a whole new scale.
It's the cruel irony of verticality. To build a super tall building, you need to house more people to pay the rent to justify the enormous cost. More people need more elevators to get them to their floors efficiently. But elevator shafts take up a huge amount of valuable floor space. Eventually, you reach theoretical height where the entire floor plan is just elevator shafts and bathrooms, and there's no office space left to rent.
The building literally eats itself from the inside out.
So we had to get creative with vertical logistics. And the solution that was pioneered in the original World Trade Center was the Sky Lobby.
This is the train station analogy, right?
It's exactly like a train system. You don't have a train that stops at every single little town between New York and Chicago. You take an express train to a major hub like Chicago. That's what a Sky Lobby is. You get into a high-speed express elevator at the ground floor that skips, say, the first 40 floors and drops you off at the Sky Lobby on floor 41.
That's your transfer station.
That's your transfer station. Then you get out and you transfer to a local elevator that services just floors 41 through 60.
Why does that actually save space? It sounds like more elevators.
Because you can stack the local elevator shafts on top of each other. The elevator shaft for the local elevator serving floors 1 through 20 can have a completely separate elevator car and shaft sitting right on top of it, serving floors 41 through 60. You are using the same vertical tunnel in the building's core for multiple independent cars.
That is incredibly smart.
Yeah.
You're doubling or tripling the utility of that empty space in the core.
And then you have even more advanced systems like the double-deck elevator, which the Petronas Towers famously used. It's one car, but with 2 levels. It loads people from the ground floor and the mezzanine level at the same time. It doubles the capacity per shaft.
Though it does have that slightly awkward social moment where if the guy in the downstairs car holds the door for someone, you're stuck waiting in the upstairs car.
Efficiency always has its social costs.
Speaking of costs and efficiency, let's talk about something I found in the research called vanity height. This was a statistic from the Council on Tall Buildings that I found both hilarious and a little bit depressing.
It's the dirty little secret of the super tall industry. Vanity height is defined as the vertical distance between the highest occupiable floor, so the last place a human can actually stand and work or live, and the absolute architectural top of the building.
So it's the spire, the antenna, the empty decorative crown. It's the part of the building that has no function other than to be tall.
The decorative hat, basically. And in modern super tall buildings, the average vanity height is nearly 30%.
30%? You serious? So if a building is 1,000 feet tall, 300 feet of that is just empty air and steel truss.
In the Burj Khalifa, the vanity height is 244 meters. That's over 800 feet of unoccupied spire. You could fit the entire Eiffel Tower inside the empty, non-functional spire of the Burj Khalifa.
That's insane. It brings us right back to those medieval towers in Bologna, doesn't it?
Yeah.
We're not building for usable space anymore. We are building purely to break a record.
It creates a real tension in the purpose of these buildings. Are we building them for density and efficiency to solve the problem of limited land? Or are we building them as national monuments and symbols of ego? Because the environmental cost of these things is not trivial.
That's the perfect pivot to the next part of our deep dive, the environmental impact. Because building these things requires absolutely massive amounts of energy.
We call it embodied energy or embodied carbon. To make steel, you need blast furnaces running at thousands of degrees, burning huge amounts of coal. To make cement for concrete, you have to heat limestone in a kiln, which releases enormous amounts of CO2 as a byproduct of the chemical reaction itself. Then you have to transport all that heavy material to the site and use more energy to pump it a kilometer up into the ski. The carbon footprint of just the construction is enormous.
And once it's built, it's not exactly a passive green structure, is it?
No, you're constantly fighting physics, you're fighting the stack effect, hot air rises. In a very tall building, the temperature difference between the warm inside and the cold outside creates massive pressure differentials, turning the building into a giant chimney. You'd have to constantly pump water up against gravity. You have to power elevators. You have to air condition a glass box that is often sitting in direct sunlight with no shade from other buildings.
It honestly sounds like an environmental disaster when you put it like that. Is there a counter-argument? What's the pro-skyscraper environmental case?
The argument is density. If you put 10,000 people to work in the Shanghai Tower, that's potentially 10,000 people who aren't sprawling out into the suburbs, paving over farmland. They are sharing infrastructure. They aren't all driving cars an hour to work. They're taking an elevator.
So the per capita carbon footprint could be lower than the suburban alternative.
It can be, yes, if the building is designed correctly. And we are seeing a new generation of green skyscrapers that are really tackling these issues head on. The Shanghai Tower is a great example. It's basically a glass building inside another glass building.
A double skin, like a thermos.
Exactly. It creates this huge 9-story tall buffer zone of air that circulates between the inner and outer skin. It insulates the building, which massively reduces the cooling and heating load. The Empire State Building, of all places, actually did a huge green retrofit a few years ago. They replaced all 6,500 windows with high-performance units and upgraded the insulation. They cut their energy use by nearly 40%.
So the cutting edge of the technology is pivoting from how tall can we possibly go to how efficiently can we operate at height.
It is, which leads us to the most surprising and, I think, exciting trend in the future of skylines. We might be moving away from concrete and steel altogether.
We're going back to wood.
The skyscraper.
Now, when I hear wooden skyscraper, my brain immediately goes to the Great Fire of London. I think of a giant pile of kindling. Why on earth would we build a very tall building out of something that burns?
It's a valid question, but this isn't the 2x4 lumber you get at Home Depot. This is a new category of material called mass timber, specifically cross-laminated timber, or CLT. They take layers of wood and glue them together at 90-degree angles to each other under immense pressure.
So it's like a kind of super-engineered high-tech plywood.
That's a good way to think of it. And it has the structural strength of concrete, but it's about a quarter of the weight. That means you need smaller foundations, which saves a lot of carbon right there. But the real kicker, and this is the part that surprises everyone, is its incredible fire resistance.
How can a massive piece of wood be fire resistant?
It's all about mass and charring. If you try to light a single thick log on a fire with just a match, it won't really burn. It just chars on the outside. In a building fire, the outside layer of a CLT panel turns to charcoal, and charcoal is an excellent insulator. That char layer protects the structural core of the wood from the heat. Steel, on the other hand, doesn't burn, but it loses its strength and starts to buckle and deform when it gets hot.
That is completely counterintuitive, but it makes perfect physical sense when you explain it.
And from an environmental perspective, it's a game changer. Concrete emits a ton of carbon when you make it. A tree is carbon. That tree spent 50 years sucking CO2 out of the atmosphere, and now you are locking that carbon into the structure of a building for 100 years. The building itself becomes a carbon sink.
Are these actually being built yet, or is this all just architectural renderings and fantasy?
Oh, they're being built. The tree in Norway is 14 stories tall, made of CLT. Brock Common's Tallwood House in Canada is 18 stories. And there's a serious proposal in Tokyo from a major timber company called the W350 Project, a 70-story wooden skyscraper planned for the company's 350th anniversary in 2041.
70 stories, made of wood.
It feels like we're coming full circle, doesn't it?
Yeah.
We started with mud and timber in Yemen and Rum because that's all we had. We moved to steel and concrete to conquer the laws of physics. And now we are using high-tech engineered timber to try and conquer the carbon cycle.
It's a really fascinating evolution of purpose. We went from building for defense to building for commerce to building these ego-driven spires, and now maybe to building sustainable vertical forests.
The skyscraper has always been a mirror. It reflects whatever our society values most at that point in time. First it was safety, then it was commerce, then national pride, and now, hopefully, it's sustainability and survival.
It really does change how you look at a city skyline. The next time I step into an elevator, I'm not just going to be impatiently waiting for the doors to close. I'm going to be thinking, I'm riding on a machine with a safety brake from 1853 that completely inverted the social hierarchy of the modern world.
And you're standing inside a hollow tube that was specifically shaped to confuse the wind.
It's all connected. As we wrap up this deep dive, I keep coming back to that idea of vanity height. We clearly have the technology to build a mile-high tower. We could probably start tomorrow if someone had the money, but the question is, should we?
That is the ultimate question, isn't it? Just because we can conquer the sky doesn't always mean we should. But looking at our history, from Rome to New York to Tokyo, I have a feeling we're not going to stop trying anytime soon.
We're just hairless apes who really, really like to stack things high, after all. Thanks for taking this deep dive with us.
Stay curious.